from University of São Paulo, USP, some years ago, and then she moved to Italy, and then a postdoc in Columbia, right? And then she moved to Geneva, where that's a nice place to do exoplanet stuff. And then got the job in Potsdam, where she is now. And with there, I mean, yesterday, we had a lot of cosmological scale. Now we go back to galactic scale, making bridges. So, please.
Obrigado. Olá, todo mundo. I will speak in English because that's the way it's set to be. But I guess everybody is from Brazil? Então todo mundo. Então deixa eu falar oi primeiro em português. Estou muito feliz de estar aqui com vocês. Eu preparei as aulas, são 4 aulas, mas tem um colóquio também, que o colóquio vai se focalizar mais nas estrelas mais velhas que a gente tem, porque elas são importantes, como a gente pode usar. E hoje a aula de hoje é mais sobre abrir para vocês o tipo de instrumentos que a gente tem que ter para estudar a galáxia e como que isso depois vai ser útil para estudar outras galáxias, ou mesmo para entender cosmologia e mesmo planeta. Então, na verdade, essas aulas vão ligar aí com os outros, espero, né? Eu não vi as aulas do Sidney, mas imagino que com o Sidney, que é colega meu lá em Potsdam, vocês já viram bastante sobre evolução estelar, né? Bom, so I am very happy to be here, and I put this thing. Our galaxy has a history, because that's the main point of the lectures. Just to know more or less who you are, who works on stuff related to our Milky Way. Okay. And so who works on other things related to astronomy? And cosmology? Okay. So, a place in astronomy. Is it wrong? Okay. Gravitational waves. Who works in gravitational waves? Okay. Okay, fine. So, so the area that I am, why I put this title, okay? So Galactic Archeology in the Gaia era. Archaeology, because we're going to use stars. So most of what I'm talking here is the stellar part of the galaxy. Of course, the galaxy has also the gas, and a lot of other science you can do with the gas. But the gas, in terms of chemistry, gives you the composition of the gas today. While when I do stars, I can have the composition of the stars all along the galaxy formation, because depending on the age of the star, the composition of the star is going to tell me a lot of what was happening at that time. So galactic archaeology, that's the reason, because you're working back in time, and you're using as fossils the stars. So that's why. And why in the Gaia era? Because Gaia is a mission, a satellite, that has been transformational for galactic archaeology, but not only, for all areas essentially, but for Milky Way is really a new game. So I have organized the lectures in such a way. In the first lecture, that's today, I give you a brief introduction of what is the Milky Way, because not everybody is working or remember, and how we're going to have to build. So the whole goal of galactic archaeology is to build the big maps of our galaxy, and we call these maps multidimensional maps. Why multidimensionals? Maps of stars all over the galaxy, hopefully, one day. We were in a very short volume, a small volume. Now we are expanding these maps, where you have information about the velocities of the stars, the position of the stars, the age of the stars, the chemical of the stars, the chemistry, several elements. So that's why it's a multidimensional maps of the Milky Way. That's the goal, okay? And for that, how we're going to get these maps, we need to combine different techniques. And the techniques, the basic that I'm going to cover very briefly, is photometry, so the color of the stars, astroseismology. People who work with planets know about seismology, so the pulsation of stars, but I'm going to use astroseismology for galactic archaeology. It's different. And also spectroscopy, of course. So spectroscopy, astrometry, which is Gaia, photometry, and astroseismology. You say, oh, you need the 4, and we're going to need the 4 things, okay? And so that's the goal of today. And then in lecture 2, we're going to use this arsenal of things to show some things happening in the galaxy. And one of these things is called radio migration. Radio migration is a secular process that happens inside our galaxy, by which it complicates our life. If you want to use the information of the galaxy to trace the history of the galaxy, it gets complicated because the stars are born in a place with a certain chemistry, but then due to radio migration, secular process, they mix. The star can move from the birthplace to a new place. And so if I study here the solar vicinity, I say, oh, I'm going to study how was the star formation history, which is what we are looking for. So the number of stars formed in enough time here. But then here, is not only the star forms here, but there are some that were formed far away and are now here. So this messed up. It's like we want to tell the story of the galaxy, but the galaxy is not anymore a fry egg, it's a omelette. It's already mixed everything. And I have to unmix so that I can tell the story. And that's the difficulty. That's lecture 2. And then, of course, a big player is lecture 3, is the bulge of our galaxy. It's the inner part of the galaxy, where we have one of the oldest stellar population of our galaxy. You have a bar, and this bar is contributing to this secular process. And this bar can kick stars from the inner parts to here. And I can find stars that were formed there in the bulge that today are sitting here in the solar vicinity. And that's what I want to show you. How do you figure out who are those migrators? We call them migrators. That's lecture 3. And then lecture 4, you see that despite we live in a moment which is the perfect moment to do this kind of science because we have an amazing data sets, we see clearly where we lack data still and where we are going to go from there. So there's a lot of challenges that we cannot address with this data. And the people that are my age now, who are working with this data, we are also the responsible generation to prepare the next. So I'm going to discuss some things we are preparing for being launched, another Gaia, for example, that to be launched in 2050, okay? So, of course, I'm not going to be the one that's going to use this data, hopefully one of you, unless I stay fit long time. Okay, so that's the idea. I hope you enjoy. So I already explained this a little bit. So what is galactic archaeology? Somebody gave me a pointer, and I forgot. I see it. Okay. So what's galactic archaeology is what I just said. Galactic archaeology wants to reconstruct the past history of our galaxy from the present-day kinematic and chemical information. And I wrote kinematic and chemical information, but I should have written also ages. The age of the stars is going to be very important. However, age, as you probably heard already from Sydney, is very difficult to get. And so sometimes we are without the ages. But still like that, we can hope to use the chemistry to kind of infer an age. So that's why I focus here a lot in kinematical and chemical information. So why is this challenging the Milky Way? I just said, because the Milky Way, our galaxy, is a mix of stellar populations. So you have stars that are mixed because of different reasons. So what are the main reasons? Secular process, meaning stars that are born in a place and kick to another place. So you mix stellar populations. What is a stellar population? It's stars born with the same star formation history. Number of stars formed per unit of time. And we know that the number of stars formed per unit of time is faster. The star formation was faster in the inner regions of the galaxy than here. So these mixed stellar populations, because depending on the pace of forming new stars, you change the chemical composition of the stars. So why is this complex mix? So this is part of the reason because of this radio migration, but also because we have, in the top of that, you have accretion. You have galaxies that fell in our galaxy. So we have accreted stars that are not part of the star formation of our galaxy. It was another galaxy that had other stars, and the stars now are here. This is amazing, because now with this data, you can figure out who is here, but it's not forming here. It's what we call the ex situ stars. Okay? So you mix with these two. And the other challenge is that we have been confined to a small volume around us. We knew a lot about stars around 1, 2, 3 kiloparsecs from us. And now we are expanding this to 10 kiloparsecs. And when we are in the halo, you can reach much more, because when you don't have dust, That's the main challenge also. And that brings me to this here. Why is even more challenging to go in the bulge? Because towards the bulge of our galaxy, you have a large distance from us, large extinction, so dust that will take the light, and not only is there in the center of the galaxy that you have the most mix of stuff. You have disk, you have a bulge component, which you call a spheroid, you have everything there. So when you want to study and tell the story, it gets complicated. And then you have to do what I'm going to show you in lecture 3. Okay, so while I speak, you can always interrupt. This is a lecture like an onion. If I cannot finish, I don't finish. So it's very relaxed, okay? I put some material to read. Maybe what I have here is not exactly what I put there. Here I added IAU Symposium. So IAU Symposium are the main meetings of our field in the galaxy. In astronomy, International Astronomical Union Symposiums. And I had the possibility to organize one in 2017 about the Milky Way. And this is collected in this volume here. And it was called Rediscovering the Milky Way. Why it was important to organize this at that point? In 2017, what was happening? We knew that the Gaia will come out with the big data release in 2018. And we knew we would be flooded by data, and the way we work in galactic archaeology will be changed for forever. Therefore, we need to know what we knew up to that point and discuss with the whole community how we're going to take care of this new data, because it will be a data avalanche. Nobody knew exactly how to work with this data. And up to that point, we are having already what was happening is that we were expanding a little bit the volume already we are studying with other spectroscopic surveys, spectra of stars. That was starting to happen, but still without Gaia. And also astroseismology, because astroseismology, which was first used for planets, actually in 2009, it was discovered that astroseismology could be used also, measuring red giant stars. As you know now, the red giants are the brightest one that you get farther away information when they are brightest. And if we get seismology from red giants, seismology gave us, with a lot of tweak, but give us an age of a star. Give us a mass and a radius of a star. You're going to see this in a while. So 2017 was a moment where astroseismology for galactic archaeology, as we call, we had been used it to show how this could change the field. And we wanted to discuss this all with the community, seismology, spectroscopy, and be ready for Gaia. And that's what we do in this volume here. So this is a review only about astroseismology of solar type and red giant stars, and I'm interested in those here, okay? Because for the red giants, you see, things are less complicated to extrapolate and get an age. And the others, this is one about the bulge annual review. So the annual reviews of astronomy and astrophysics is also an important publication in astrophysics. You are invited to write a review of a topic. And here, with Beatrice Barboui, we wrote one about the bulge just before Gaia and Apogee, which is also is a spectroscopic surveys that peers in the dust and get to the bulge. So you see that 2018 was really transformational because you had seismology that was already we were learning how to work with it. Then Gaia came up, and then also we had a spectroscopic survey like Apogee. So it was really nice but stressful time. Okay, so galactic archaeology, as I said, there is this huge complexity, so you're going to need to use all these tools that I told you. This internal process that I said, like bar formation, gas flows, stars accreted from mergers from other galaxies, and then moving from their birthplace, all this can also, we have also triggered star formations of when the Magellanic Clouds passed the Milky Way in the past, or even the Sagittarius dwarf, which is also a dwarf being accreted in the Milky Way. They can not only accrete the stars, the Magellanic Clouds, but the Sagittarius, we have stars inside our galaxy that we know are for Sagittarius, but you can also induce a star formation. So when a satellite crosses the disk and there is gas, you can make star formation in situ, so here, forming stars here, because somebody passed. But you can figure out those too, because they are not part of the star formation of the Milky Way. So you see the complexity, right? But this you have to account too. So this is why galactic archaeology is so now used. And you have a general, another field, which is the field of simulation. From cosmology, from the beginning of the cosmological structure, to come up to the galaxies we see today. But then you have to model the baryonic matter, so the stars. And you have a problem, because you have a problem that we call the subgrid physics, which is how you're going to model the formation of stars. This is an open problem, and therefore, it's very difficult to reach final conclusions only from cosmological simulations, and galactic archaeology and cosmological simulations talk to each other. Because from the Milky Way, we can get constraints to constrain the simulations, because to see if what is coming out from the simulation makes sense at all, okay? And so the difficulty to model the star formation is one of the reasons why galactic archaeology is so important, because you can use data from the Milky Way to constrain also cosmology. So the Milky Way can provide extremely useful constraints. And for the Milky Way, if we have orbits of the stars, the chemistry and the age for large samples at all ages, then we are in the game, okay? However, this is an idealized situation. And as you see, we have this, sometimes for small sample, but then they are too close. And then we go for large sample, we miss one. And so the art here is to be able to work with different samples, having different information for a common goal. In the end, the answer has to be similar, but you have to. So that's what I say is to work on the Milky Way data like in shells. You have to see what is your question. I can tell you use this data. You know, that's the main thing now. Okay, so stars then is what we are going to use as fossil records, not the gas. Okay, so just to remind you, what is the Milky Way? This is a cartoon, of course. This is a new cartoon made by the people of ESA Gaia. We usually all to show the cartoon made by this picture by the US. Now we have one from the Europeans. So here is how we think our galaxies. This is more or less where we think the spiral arms are, the inner arm. Then you have a bar there in the center. Our galaxy is a spiral with a bar. The sun is there, and this is 8.2 kiloparsecs, the distance between from here to the central black hole that we have in our galaxy. And this is in light years if you don't know. But essentially everything, of course, I'm going to talk about kiloparsecs, okay? And this is, of course, a cartoon. To make this map is already science. Because to make this map, you need a lot. And you need what? One of the key points is to compute precise distance. And it's not an easy thing to compute a precise distance. So astrometry measures to you the parallax, right? You all know about parallax. Essentially, you see this with your eye. If you put your finger here and you see the difference in angle that makes, this is parallax. So we use this and the movement of the Earth, and Gaia used this to measure the parallax. Now, if I inverted the 1 over parallax gives you a distance. But this is only for exquisite parallaxes. And Gaia has exquisite parallax, but the uncertainties in the parallax diverge. And so because you do 1 over parallax. And so it's not enough to use 1 over parallax when you want to do the galaxy. Because the uncertainty starts to extrapolate and gives you nothing. And so the only way you can do is like, when the parallax uncertainty is getting big, you have to add some other information to tell the code that's computed the distance to say, okay, the parallax is not giving me holding anymore my distance. What else do you have for me? And what else is photometry? The photometry is going to give you the colors of the stars. And so it's a way for you to handle the dust, because the dust makes the stars redder, right? And the other thing, if you have a spectroscopy of the stars, then you can also know the temperature of the stars and the gravity of the star. So this, again, helps you. So when you put the 3 things together, you beat the problem of uncertainty in the parallax, and you can still use the parallax, still important, and you can increase your map. And that's what we're going to do, okay? So we want to map up to the bar, at least. That's the goal. And we have been confined here in this little ball, yellow, which is the sun. Okay, if I look our galaxy edge on, we have a disk. In the middle, we have the bulge. That's what you're seeing there in this cartoon. And our disk is warped. That's also a measure today. And we have there, in this insert is showing, this insert of the disk is showing that we have in our galaxy a thin disk and a thick disk. the way the words explain, a thing and a tick. So the thin disk, the velocity, the rotational velocity is at this position is 220 kilometers per second, and the thick disk is, of course, lagging the thin disk. It rotates lower than the thick disk, than the thin disk. So we say the thick disk lags the thin disk. This is important because the velocities of the thick disk are different than the velocity of the thin disk, and they are more thick than. The scale height of the thick disk is thick, okay? And the thin disk is thin. That's why it's called like this. This is very important, and as you're going to see during these lectures, this holds a clue about the way our galaxy form, and a lot of debate in the area because of this. So this is also a cartoon, and we need the precise distance. So one way to get precise distance, and I don't know if you saw this with Sydney, we have one kind of stars that's called Cepheids, are variable stars. They have periods, and using the Cepheids periods, I can get good distance. They are bright, and so I can get distance far away. The only problem is that they give me a population of stars, a family, that is young. They are all born yesterday from the time scales of the Milky Way. So this gives me the present time distribution of something, whatever the Cepheids can give me. Advantage, I have the distance. Disadvantage, I don't have the age baseline. They are now, okay? Millions of years, which is nothing. But if you use the Cepheids that you can go very far away, you have this paper in 2022, for example, beautifully. This is the distances, or the y. So imagine you see in the galaxy from above, you have the x and y. So this is like radius, more or less. And here's the height above the midplane. And you see that what I show you in the cartoon, that the disk is warped, you can see here in the Cepheids distribution is warped, right? So this is a great way to do a map far away. But we want more. We want a map far away with a baseline in age. Now complicates the problem, right? Because age, Cepheids gives me the age for free because I know they are young, because who they are. They are variable stars, they are young. So I don't have to compute the age. Okay, so one thing that's complicated to model our Milky Way is this. First of all, I'm going to show you one example of a simulation done by another group. For example, here, a group I took from Korea. They is doing a disk, only the disk, isolated disk, anybody simulation. And this is what you see. You should see a galaxy simulated from above. You see in face on, and you're seeing the galaxy edge on. And you see that you have this is what I'm called secular process. You see that you will start forming a bar that in the inner parts of the galaxy, in the bulge of this galaxy, and you start pulsating things. And this is how you see the bar as face on. You see this is pulsating now. You see. And these processes, they can lead to the stars moving from where they were born. And so what is happening at this position here feels what was happening there. And so that's why it's complicated. You cannot say, I'm going to study the Milky Way here in the solar vicinity. No, because everything that's happening in the solar vicinity also is feeling what was happening there. So it's not so easy. And this is a simulation difficult to do. You see, this is not so old. This is 2017. And this is an isolated disk. Only anybody, so without gas, only gravitation. Now, you can make things more complex by putting gas, hydrodynamical simulations, right? And here I have another example from 2019. This is stars and gas. You see the gas here, and you see the complex structure that's forming in the inner parts of the galaxy. You start forming the spiral arms, but in here, you have this flocculent star formation is a mess. And this is very difficult to model. That's what I say. Today, nowadays, the best simulation is still have trouble to do a good star formation and to have a good bar and to make a galaxy that really can be called Milky Way-like galaxy. So a lot of simulations have Milky Way-like galaxies, but are they really Milky Way-like? How do you define a Milky Way-like galaxy in the simulation? So all this is the complexities that give. And you see in the end what is happening in the simulation. You're forming a kind of a center star nucleus here. The nuclear disk is gas here. I'm showing you gas, not stars. And you have this nuclear disk of gas forming here. But you're not seeing the old stellar population that's in here around, which is the bulge, okay? So this is the end of structure of a simulation, isolated, okay? Isolated, meaning no merger with another galaxy happening. Now, look how beautiful. The inner disk is forming this nuclear disk, as we call in our galaxy. We also have one. Difficult to see because we are inside the galaxy, so it's difficult to see our nuclear disk. Beautifully, with JWST, you can see them. Look at this galaxy. This is now not simulation. This is reality. Reality with JWST. JWST has resolution, spatial resolution, and can see in the infrared. So you can beat the dust. And now you have this amazing, I even got this when I see this image because I found it so amazing. Look at this here. Look at the flocculent gas. This is showing me some gas. Look beautifully at the ring. It looks pretty similar to some of the simulations we saw. So this is James Webb Telescope, the 19 nearby face-on spiral galaxies that they have measured in near and mid-infrared light. So they could peer the dust and show us this. And this is from the FUNGS team, and show this complex inner region bar devoid of gas also. You see a place here, you lack gas. You see? The gas is swept away in the inner parts of the galaxy. All of these matter to us. Here is a zoom in one of these galaxies. So look how beautiful, okay? So now the complication is the galaxy, the two simulations show you the galaxies are isolated, but reality is not like that. We know we have other things falling in our galaxy, and actually one of the biggest discoveries of Gaia right in the beginning was the Gaia Enceladus galaxy. The Gaia Enceladus galaxy was a massive galaxy that collided with ours 10 billion years ago. Okay, and we can see this clearly in the data, you will see later. So the reality is that I need a cosmological simulation with a merger history that's forming a spiral galaxy with a bar. All this is very complicated because you are sampling different scales, enormously scales, and you need the resolution and all of that. We are getting there, but we're still not there. So here I'm showing you one of the most updated simulations, so 2024 here, by the group Grant et al., where they have made available these simulations, which is a cosmological simulation that they have also gas. And here you see, here the stars and here the gas, face on and edge on, face on. And you see the mergers come. You see these little things are mergers. And this is, you see the bar is forming, sort of bar. There's a lot of discussion how these bars form. And this is mergers, gas accretion, and more. Everything is happening in our galaxy. This is our galaxy history. And this is what we are trying to model. So as you see, it's not simple, right? And you want good, precise data, and you're going to need to use whatever you can to figure out this history. Now, to make it more complex, I go one more complex step, is this. You have a cosmological simulation, as I show you, has gas, has stars, has a bar, maybe. But now, our galaxy also apparently depends what happens to our history of where we are in this universe. And we know we have a big galaxy next to us, which is M31, Andromeda, no? So now there are this kind of simulation, which is the high-resolution environmental simulations, which, for example, this HESTA simulation that's made by my institute, where here you have a simulation of what a volume where they thought they are seeing a Milky Way and an Andromeda. And now you have to simulate this. This is a simulation of that particular volume of this cosmological simulation where our galaxy and Andromeda is. For example, here you see a big spiral here, another spiral with each one of these spirals has its own satellite galaxies. This is how Andromeda is, how Milky Way is. We have a lot of satellite galaxies. One of the most obvious is the Magellanic Clouds that you see. So now, for example, the HESTA simulation has other problems, has not the resolution inside the galaxy that we need to get the bar that we need to understand. You see, so that's why I'm not working simulations. So anyway, okay. So how are we going to tell the story then if we have this mess happening to our galaxy? Can we still say something? And the amazing thing is how much we can say. And this is what I hope to show you. It's amazing that is in this mess, a lot of things behaves well. And we can understand and can extract the history of what's going on. And why is this? Because the Holy Grail is the chemistry. Once a star is formed from a gas place that has been enriched, this gas is enriched because we started the periodic table with hydrogen and helium, right? Some lithium, some deuterium. After that, you need the stars to make the rest. So in the beginning, at some point, the star was formed in the region inside the bulge, and another was formed here. Well, the number of stars formed per unit of time is different there than here. So there, in a certain time, the gas was more rich with chemical elements. And here, in a place where it's low, the gas can be more poor in chemical elements. But once the star formed in its outer parts, the atmosphere of the star, where there is no process going inside the star, that composition is preserved, especially for some chemical elements, preserved. So now I take the star that was in the bulge and put it here, and I can, from the chemistry and its age, say, oh, this star cannot be from here. And I can see where it could have come from. Only because of the chemistry, because the kinematics of the star is changed. Okay? So because we have our Holy Grail is like a time machine. And that's why the Milky Way plays a role here. Because to measure good chemistry, you need to be here in the galaxy. We can get chemistry for other galaxies, and we are start getting some even chemistry somehow for JWST galaxies, but they are very, very difficult in certain small elements. Here, we have the completely chemical picture, okay? So, now that I show you where we're going to sit with our lectures, I wanted to make a detour to show you the basics, that we cannot go on without the basics. And this is what I call detour chemical clocks. Because it's difficult to measure age in stars, we sometimes can use abundance ratios. So one element divided by another element, and this will give me an idea of time scale. And this is the key. And why is that? Because elements are forming. So here I put some figures that I have made in 2004 for a Sky and Telescope article that I could not download myself, so I don't know how to get. I think I had it at some point, so I put in the material, I gave the PDF of another one that I wrote for American scientists. Yeah, American science. But for the Sky and Telescope, we did some nice pictures. And this is to illustrate this. So large stars make, for example, oxygen and other elements, because you need all the building of the chemical elements to happen. You need a more massive star so that you achieve all the burning process that you go from helium up to iron. After the iron, you cannot do this burning anymore. You're going to explode. So you have the type 2 supernova, the ones that explode very quickly, have a short time of evolution, and come from massive stars. Massive stars are stars that are between 8 and more the mass of the sun. And then you have this other system here, which is a type 1a supernova. This is a red giant that throws material into a white dwarf, and then you have an explosion. So this is a type 1a supernova, and this takes time. This doesn't take time, this takes time. So the main product from this explosion is iron. I'm taking this as to make it simple. The main product of this is iron. The main product of this is oxygen. But I said this one dies quickly, this one takes longer. So what happened? That's what we use here. If I plot oxygen over iron versus iron is like time, okay? It's not linear. But as I said, you need several stellar generations to enrich the chemistry. So as you increase in iron, you increase in time. We will see this is not so simple because it depends where you are. But for now, iron is like time, and then I make oxygen over iron. Every time I show something, maybe Sydney already explained, in brackets mean with respect to the solar. So if the sun is here, solar level is 0, 0. Okay, the sun is here, okay? So here, when I am minus 1 over 10 the metallicity of the sun, I am more like halo stars in our galaxy. And I observe that all of them has oxygen over iron, a plateau here of a certain value. And later, the thin disk stars, after this minus 1, and our sun is in the thin disk, this thing starts going down. If I plotted the data, you'll see now. Why is this happening? Because oxygen is released immediately. Iron needs time. And so that's telling me, oh, these stars in the halo had a very fast star formation. And so I didn't have time yet to throw the iron from the type 1a. So I'm forming the gas from the amount of chemical elements that you have from massive stars. And this gives you oxygen over iron a certain value, because the massive stars also make iron, but in that proportion. Once the type 1a start dying, a lot of iron is injected in the interstellar medium, and these things start going down. Okay? So when I take a star like the sun, I see, oh, the sun was born into a gas that had already a lot of iron from type 1a as well. This is key, okay? Now that I know this, I can transform and look to this. If I plot oxygen over iron versus iron, same thing. And then I plot stars from different places. The solar vicinity stars are here. If I go to bulge or elliptical galaxies, they tend to have high oxygen over iron. Meaning, in these galaxies and in these bulges, the star formation is so quick that the type 1a didn't have time to contribute yet, and the stars are already formed. So they formed with a typical imprint of massive stars enrichment. Okay? That's why oxygen. And if I go to the Magellanic Clouds, it's the opposite. Nobody has high oxygen over iron. Everybody is low. Why? Because there the star formation was like slowly. It was a not efficient star formation here. So by the time, so here the bulge, by the time I was already with solar iron, 0, the type 1a still didn't have time to enter the game because I reached solar quick. The type 1a didn't have time to contribute. In the LMC, I was so slowly in producing that even at -1 here, the type 1a were already contributing. Because I was there doing slowly, so I had time to the others to die and then contribute. This is a key. If you haven't understood this point, please ask, because that's the main thing I'm going to use from now on. Okay? Yeah.
Which kind of stars produce oxygen?
Yeah, these are the type 2 supernova, and they are massive stars that are between 8 and the maximum mass, which is 100 or whatever. Yeah. And the type 1a are binary systems where you have 2 intermediate mass stars. And one will become a red giant, will throw the mass, and the white dwarf, and then they explode. Okay? It's one of the scenarios. Okay. Okay, so this is the idea. So the sun, the 0, point, this is a very nice image, by the way. This image of the sun was taken by the solar orbit in March 2022, when this spacecraft was halfway between the Earth and the sun. Beautiful, no? This is one of 2022 image of the sun. I love this image. So essentially, this star, our star, was born 4.6 billion years ago. For the sun, we have age, because the sun is sitting here next to us. We can measure the age in different ways. The composition of the gas from which the sun was formed, the sun, the outer part of the sun, is showing us the composition that the gas that formed the sun had 4.6 gigayears ago. Okay? The sun was formed from a cloud that had that composition 4.5 gigayears ago, billion years ago. This is what I'm seeing when I look to the sun. And this is preserved in the photosphere of the sun. It hasn't changed, the chemical elements, mostly. Okay? So the sun is our first fossil record. Now, what's the different nucleosynthetic sites? Because this sun, as you'll see in the next slide, you have several chemical elements here. So what is the composition of the universe? We have most of this is hydrogen, a little bit of 25% of helium, 24, and the rest is what we call metals. Everything that's more heavier than helium. Okay, so hydrogen and helium, then metals. For astronomers, metals is everything that's above helium. And these metals here, which is 1.39%, really small, is divided into these chemical elements. So we have a lot of CNO. We are made of CNO, by the way, a lot. So we have that composition, more or less. And then, no, we don't have neon, but okay, we have iron and so on. Here are what we call the alpha elements that are made by addition of alpha particles, so magnesium, silicon, and oxygen. These are the main alpha. And then the iron and iron peak elements. Here you have the iron element. This is the way the metals are distributed in the universe. And this is a nice Asplund paper where he discussed how do you measure this. These are abundances measured in the sun. Okay? The solar composition is this one that you're seeing here. So the sun then will die. How? as a planetary nebula. It will form a planetary nebula. It's not going to be a supernova. It will eject its outer parts, and you stay with a central star in the beginning, in the middle. When it will eject its gas, what is in this gas? This. Okay? We are measuring now in the sun photosphere, but they will be ejecting. And this will come to the gas. And new generations will form with this composition. Okay? Plus the rest that's coming out. So, by the way, this is also a beautiful image. Is the solar dead, so we form a planetary nebula. In this case, I'm showing the ring nebula that was observed by JWST with high. So the JWST is so amazing that you can observe in other galaxies high redshift, you can observe in the planet's atmosphere, but you have such a beautiful resolution that you can observe something like a planetary nebula. And what is amazing, if you go to these photos, if you go and check them online, you would see that sometimes behind an image of a nearby object, you see a galaxy. It's beautiful. You can see little galaxies behind the image. Okay, so the stars like our sun, they will do this, become a planetary nebula and eject these elements when dying and leaving a white dwarf in the middle. Now, the other is the type 2 supernova that I told you, core collapse supernova. And this is also a beautiful image that I put here. Is from the MERCAT, which is in radio image, where you see supernova remnant of an explosion, and more massive stars than the sun, 8 times, I wrote here, will explode as core collapse supernova, and most of, will make several elements, but a typical element is oxygen. That's not made by the sun, okay? So actually, that oxygen that you saw in the composition of photosphere of the sun was not by him. It was made before, for earlier generations than the sun. That's important. So then I'm saying here that the stars, like the sun, but that are in binary shifts, can form a type 1a supernova. I already explained. And if 2 neutron stars merge, then they can also release some important elements, among of them the most heavy elements we have in our universe. And that's the amazing thing about gravitational waves and the studies that are being possible now to see this formation of these chemical elements, and maybe with statistics of events, or even get the stellar yield, how much each of these events contributed, so that we can put this in as part in a chemical evolution model that you see right now. So this is the composition of the sun. We show typically this in this weird scale, log with respect to silicon. But essentially, this is because the amounts, the magnitudes of the amounts of the elements is huge difference, right? As I saw, all the maths were 1.3%. So this is the composition of the sun. And here you have hydrogen and helium made by primordial nucleosynthesis, so Big Bang. Then here, these elements CNO made by CNO made by helium burning, then carbonyl burning, then oxygen burning, then you achieve to the iron peak. To go beyond the iron, you're going to need something else to form the N capture elements. And here you're going to have what we call the S and R process, the slow and rapid process formation, where you accreted neutrons. And this, how you form this, not inside the stars, so either in the merger of 2 neutron stars, or also in the explosion of a type 2 supernova. And there are amazing things you can say about the early universe when you study these elements here too. A lot of what we're going to do is here, because when you come to these elements, you need more signal to noise, you need high resolution spectrography, and so not every time you have this. Most of the elements, we're going to have the more abundant ones sometimes, and we're going to have to deal with that. So as a summary, I put for you here this beautiful NASA periodic table, where here is the main process that I discussed with you. So white dwarf supernova, a type 2 supernova, then merging neutron stars, and each element that's dominated sometimes is produced by 2 of these kinds, and also the main made elements in the periodic table. It's a kind of a summary. Okay. Now you know more or less how the elements are produced. Now I have to tell you who are the fossil stars I'm going to use. And this will be which stars are good for me to trace the history of the Milky Way. Stars that can have all the ages. Because if I use only the Cepheids, as I show you, I'm seeing the Milky Way today. But I want to see the Milky Way in the past. So I need the stars that have a long age baseline. So who I'm going to choose here in the diagram. So in this CMD that you saw already with Sydney several times, so you have temperature here, and a luminosity, and after we're going to have essentially log the gravity of the stars. So here you have the white dwarfs, here the main sequence, and the giants that are the bright ones that I'm going to use a lot because I want to go away. And so the stars, like our sun is here, it's an FGK stars. These are the ones I'm going to use, stars FGK, in this range of temperature. You see here between 4,000 and 6,000 more or less. I'm going to sit here in this kind of stars here, this and this, because they are good age baseline. Okay? They will tell us the history of the Milky Way. When I am sitting here in these stars, of course, the luminosity is in the scale of the sun is not so high, so I can see only those that are nearby, volume 1, 2 kiloparsec. But I want to see 8 kiloparsec. Either I have a big telescope, but if I don't, I'm going to have to use the giants. Because then, as you see, I can go further away. These are lines of distance. No, this is line of solar radius. But essentially, I can get to a distance far away if I use the giants. Depending if I have in high extinction, if I want to look like this to the disk, or if I can use to the halo. For the halo, I can get much larger distance. To the disk, I can get to the bulge. So this is our fossil records, okay? They're going to use. And we will focus in these longer-lived stars. I'm going to give you a list of supermarket of what can we learn from these stars. So these stars, with lifetimes spanning the whole galaxy history. So we're going to have stars young up to 13.7 billion years old. Not 13.7, but 13 point something, okay? The oldest holy grails that we're going to have. Most of them with chemical abundance from the gas from which they were born. Because some stars pass from process that can change, unfortunately, the photosphere abundance. And then this disturbs our clocks and everything. But we can figure out who are those, where are they, and we can deviate from them. And then we can then translate the sky view that we're going to show you in all what we need, 6D phase space information. 6D phase space information means 3 velocities, 3 positions of the stars, thanks to Gaia. Then, thanks to Gaia, and if we have the radial velocity, we can compute then the energy, for example, the angular momentum, the eccentricity, the maximum orbit with respect to the main plane of the galaxy, all these parameters, the integral of motions, and then we can trace also past events in the galaxy by using this phase space information plus chemistry. We can trace the galactic populations back in time using also chemical clocks. We can trace inside-out formation of the disk. You're going to see our disk form faster in the inner parts and slower in the outer parts. We can observe the secular process that are happening, which are stars moving from one place to the other. We can observe that. I'm going to show you. We can see the disk flaring and warp that you saw already with the Cepheids. We can compare the old Milky Way to what we see at high redshift. What we are seeing at high, imagine our galaxy at redshift 5 in the beginning of the story. So 12 giga-years ago. We cannot observe our galaxy. We can observe our galaxy 12 giga-years ago. Are the stars that are 12 giga-years today, right? And so how I relate this to JWST? Well, when I'm looking somebody at redshift 5, this somebody is forming the stars. These stars are formed there. But the only problem is that I don't know what I'm looking, if this will become a Milky Way or something else. But I can have an idea, no? So this is a link to what we see at high redshift as well. We can compare then our present day Milky Way with also other galaxies, like the other ones I was showing you in the nearby universe. Because we are seeing our galaxy from inside, but then I look at another galaxy like I show you, and I see the nuclear ring, so I imagine ours also has. So we are sitting between the high redshift, other galaxies, and stellar evolution. That's why the Milky Way is my favorite. And then we can, another bonus we can have, we can constrain nucleosynthetic sites. To make that periodic table I show you with these elements make like that, this other element make like that, this is also something that has used a lot of Milky Way data so that you come to those conclusions. So the Milky Way play a role there. And finally, we can do something very nice. When we go to stars that are very metal poor, 1 over 10,000, the metallicity of the sun, we are seeing then the gas in the very beginning. And then we can learn if the stars that were enriching this gas were different than the ones that are today. This is an open field as well. We call the first stars. It's also a very nice field to study. Okay, And I will finalize this with this. These are, for example, as I said, the different, here we see, again, here the periodic table. These different ways to form chemical elements have different time scales. I gave you the more example between the type 1a and the type 2. But there is the intermediate mass stars, which is also longer time, and so on. So we can play with that. And then if I take one, like oxygen and iron, and I divide them, they will depend a bit on the age of the stars. But it's difficult to get the age of stars. And to show that this is really true, there is this, for example, this kind of work here, where you can take what Sydney just explained you, the clusters. So you observe an open cluster. An open cluster is very important because it's a coeval stellar population. Has one metallicity, that open cluster, and has a whole bunch of ages, right? Because you have the sequence of the age in the open cluster. So now if I have a high-resolution spectroscopy for some of the stars in this cluster, the brightest one, and I have the age of the cluster that I can get from photometry, and I can put the two together, I can then see if what just I told you is true, that different elements. So here I have in this X-ray axis, ages of the clusters. Each point here is a cluster. For each point of this person, Casamiquela, Laia, she measured different chemical elements. Here, in color here, alpha elements, iron peak elements, then we call odd Z elements, light S process, heavy S process, SR process, different nucleosynthetic process. I'm not going to enter, of course, into detail here. So you take an element, for example, let's take one. Yttrium over, what is written there? Yeah. Yttrium over aluminium, right? Yttrium over aluminium. Let's take the, let's take yttrium over magnesium because the one that really works. So yttrium, I go here, okay, yttrium S process. Okay, S process. Magnesium, alpha element. So this is in a longer time scale because the S process is coming from low and intermediate mass stars. And then magnesium is coming from type 2 supernova. It's coming fast. So yttrium over magnesium is a good idea because this will fill the age. Is this true? Then I plot my yttrium over magnesium well measured in a couple of stars per cluster. So each point of this has 7, 8 stars is a mean. And I measure them. And then I get the age of the cluster. And this is age. And look how beautiful. You see? There is a relation, abundance ratio, age. In the ideal world, if this would work perfectly, I didn't have any more a problem to get ages of the star, which is one of the main problems that you have been here in the lectures of Sydney seeing. The problem, as we're going to see, is that the galaxy doesn't make our life easy, and these clocks, sometimes they vary depending where you are in the galaxy. So they are not real clocks. So they can have weirdos like this stuff. But essentially, you have an age. So the chemical clocks, they sit on different nucleosynthetic families, and they are proved to work, some more stronger than others. This is one of the best, yttrium over magnesium. And now, finally, I wanted to show the same plot I showed you before. So if you take oxygen over iron versus iron, and here I said two systems that form quickly, our solar vicinity, the Magellanic Clouds. If a star has winds, then this thing can go down even more, because you could have differential winds that could change this, but let's forget about this now. And now it comes the last important thing I want to show you, which is the fact that, because I have now only 5 minutes, is the IMF. I show you that different stars make different chemical elements. We're going to use them as chemical clocks, and this is how we're going to do from lecture 2. The thing is, like, massive stars, there are very few. Stars like our sun, there are a lot. So massive stars contribute a lot of chemical elements, but there are few. Our sun contributes with very small, but there are a lot. And this a lot is the IMF, the initial mass function. When the stars are born, they are born with initial mass function, where the stars like our sun are very common. Stars that are more heavy than a certain number are very not common. And this is changing this plateau here. This can move this value here, 0.4, up and down depending on the IMF, okay? And here, as you're seeing, the more efficient you are in star formation, you're going to move where this knee is happening here. As I said, if you're very fast formation, you're going to move in iron before you go down. If you're very slow, you're going to not move much in iron and you go down. This is the knee of this relation. It's giving you an idea of star formation efficiency. So there's a lot of information in this plot. And this is the plot now showing you the lockup material. So the stars die and leave some material, remnant. So you have different IMFs. So here are different scale, Cropa, are different IMFs, because it's very difficult to see what is really the IMF of our galaxy. It's a whole topic. But if you have an IMF, you can compute the fraction of the star. So here you are seeing that the massive stars between 8 and 100, they are producing here, depending on the IMF, between 10 and 20% of the chemical elements. While the stars here in the intermediate massive stars are producing, even though they are producing small per star, in the IMF they produce almost the same amount that the other ones. And here is what is lockup material, stars that became remnants, the part that's not coming back to the interstellar medium. Okay? So this is the end of the tour. And I think I will finalize here today. I don't know, the time is I think is enough for you. Okay? Good. Tomorrow we continue and do really chemical evolution and use that to tell the story of the galaxy, hopefully.
So, thank you, Cristina. So we have time for questions. Okay, Bruno over there.
Pode perguntar em inglês ou em português, como quiser.
Good.
Hi, Cristina. Thank you for the lecture. So, can you tell me a little bit more about the temperature of depletion and what is the main elements are suffering by this process? I believe it is the most fundamental element because the temperature is high and depletion of the element and the abundance on the galaxy.
The stellar evolution depletion you're talking about,
yes.
In a star, so the abundance that are not preserved. So when you are in an intermediate mass stars and you cross a certain time of your evolution, you can start having what is called the dredge-up process. The dredge-up process is when you dredge it. So you go down and you bring material that's from the inside. And material that's from the inside is burned by the star itself, or is in this connection between what's not burned and what's being burned, and this can change your carbon and your nitrogen, unfortunately. And unfortunately, because then you can use, the more you are in intermediate mass stars, for example, the more massive you are, so if you are 3, or if you are 2, or if you are 1, then this process depends on the mass. And when you are a very small mass, 0.8 or so, is not changing much. And so by the C over N, you can tell more or less also the mass of the star. So I'm talking here most of the elements that are not changed. But if I go to the giants that I'm going to use, I know that C and O can be changed, especially carbon, nitrogen, right? And this is one thing. Another thing that can also change this preserved information and is also the diffusion process. That is, you have a star, and when the star is in the semi-D down here in the dwarf region, you can have a strong diffusion process. So elements that, because the chemical elements have different molecular weight, some go down. And you would think this star is poor in those elements, but actually is not. It's the diffusion process that's happening. And it's a process that affects less the giants than the stars here. So, and lithium then is one clear, where lithium is totally burned by the star, and then you lose lithium, and so that's also something. If the star has crossed an age, lithium has gone down and is depleted. So you cannot use lithium for tracing. You can use the upper envelope of the lithium distribute of the stars having depleted to tell something about the story of the Milky Way. So this you have to be aware. So when you are using chemical elements, you can have really this depletion process that will change, unfortunately, our holy grail, which was the composition preserved. But we know which these elements are, more or less. And so it's not a problem. If you know, you can even use this fact as an information.
Okay, thanks.
Another question? Over there. Okay.
Oi, Cristina, obrigada pela aula. Eu queria perguntar daquele último gráfico que você mostrou das idades, né, do cluster. O anterior. Anterior. Esse.
Sim.
As idades, pelo que eu entendi, posso ter entendido errado, aí é um cluster só e várias medidas diferentes desse mesmo
Não.
das estrelas, ou não?
Cada ponto é um cluster.
Ah, cada ponto é um cluster.
E um cluster de diferentes idades. Como você pode ver,
tá.
um dos problemas de usar o cluster para isso, o cluster é legal porque você consegue determinar a idade dele
Sim.
fitando a isócrona que você está vendo. Mas o problema do cluster é que a age baselines dos open clusters, ela não é tão grande assim. Então, quando você vai medir os open clusters, você vê que um monte deles é jovem, mais jovem que 1 gigaano, e alguns pouquinhos são mais velhos. Porque os clusters eles são destruídos durante a evolução da galáxia. Eles se quebram e as estrelas viram de campo. Então, esse é um problema. Ele é bom, mas tem esse problema. Então, como você vê aqui, tem um monte de pontinho quando você está aqui até 2 giganos, tá vendo? Que aqui está 2 e 4 giganos. Passou de 4 giganos, acabou a história. Entendeu? Então, aí empipinou. Aí você vai precisar de outra coisa para ir adiante.
Pode usar os globulares?
Pode usar os globulares
Que é mais
também.
velho.
Aí nos globulares a coisa empipina mais ainda. Porque aí dos aglomerados globulares, o que são os aglomerados globulares? São grandes clusters, certo? Que se formaram, a maior parte deles velhos, né? Então, aí você tem a baseline velha. Só que os aglomerados globulares, que as pessoas achavam que eram simple stellar populations, hoje em dia se sabe que não é. Tem first and second, tem primordial and secondary population. E entre a primordial e a secondary population, muda a química de vários elementos. Mas você pode saber quais elementos que mudam também. E aí você pode usar, nós vamos usar ele quando a gente falar do Bohr. Aí você pode. Mas para esse tipo aqui de coisa, você vai dar algum pepino para fazer o
Obrigada.
clock.
More questions over there? Okay. You flip the side, right? Okay.
Quando a gente teve a palestra da Beatriz, ela nos comentou que existiam simulações que estavam mostrando a Via Láctea formando uma barra antes de formar um bojo. E pelo que eu vi ali, pode até, foi uma coisa que tu nos mostrou. Mas isso não seria muito mais facilmente resolvido fazendo justamente esse tipo de medida? Quer dizer, se a gente medir o alpha enhancement, sei lá, da barra e do bojo, o que a gente vai esperar não é ver um bojo mais velho do que uma barra? Então, se puder comentar sobre isso.
Sim, essa vai ser exatamente a nossa lição 3. Aí eu vou contar uma coisa para vocês, uma coisa que aconteceu recentemente. Para você ter esses chemical clocks, você tem que ter um telescópio grande que possa medir estrelas lá no bojo, certo? Já complicou. Ele tem que ver no infravermelho, já complicou 2. Vai ter agora o MUNS, vai estar num 8 metros e vai medir no infravermelho, você vai chegar lá. Aí você vai fazer espectroscopia no infravermelho, já vai complicar mais, porque tem um monte de problema na espectroscopia no infravermelho. Aí você mediu. Aí o problema é o seguinte, você mediu quantas estrelas? Porque se você mediu só um pouquinho, aí você não sabe se é uma do disco que está aqui na frente, se é um pedaço da barra, se ela estava no very old spheroid. Então, quando você chega lá, tem uma mix de stellar population. Então, você não precisa de uma ou duas estrelas, você precisa de milhares, com órbita. Aí você usa a órbita e vê, essas estão na barra, essa está no bojo, essa é o disco que está passando lá dentro. Aí, quando você tiver estatística e boa espectroscopia, você poderia. Nada disso está acontecendo ainda. Tá? Então, aí tem um jeito que é mais curto e era muito melhor, que era uma missão de satélite para o ESA, que nós postulamos e fomos escolhidos, que é muito difícil esse processo de você ser escolhido. Fomos escolhidos para uma missão espacial que chamava HIDIN. E a missão espacial HIDIN, que a gente desenhou e foi escolhido até a fase 0, eles escolheram cinco missões da ESA, e a nossa foi escolhida, só que depois, para a fase A, tinha uma concorrência e escolher só 3 e a nossa caiu, porque a nossa era a primeira que estava, é a primeira vez que estava. Os outros já tinham ido, já tinham caído, já tinham ido, nós ainda vamos de novo, eu acho. Então, nós caímos fora, infelizmente. Então, o que o HIDIN queria fazer? Queria fazer sismologia, que dá para determinar a idade, no bojo, em dense fields, ou seja, primeiro a gente ia fazer sismologia aqui em globular cluster, aí ia entender melhor a stellar evolution, dos aglomerados granulares, e com essa melhor entendimento da stellar evolution aqui, a gente ia para o bojo, e eu tinha escolhido um field na Bader's Window, onde tem menos extinção, porque o Heydin era no óptico, e a gente ia conseguir 70 mil estrelas que estão exatamente no Red Giant Branch, onde dá para medir sismologia. Então, eu ia ter idades para 70 mil estrelas na missão que ia subir em 2038, e, de repente, sei lá, em 2040 ou 45, as idades do bojo estavam saindo. Só que nós não passamos, né? Então, vai ficar para quem? Vai ficar para o ELT, o Extreme Large Telescope, equipado com um bom espectrógrafo, que vai conseguir ir lá no bojo, mas aí não vai ser um monte de estrela, né? Tem que ver como é que vai ser. Aí vai pegar lá no bojo, ou o WST, que eu vou discutir com vocês, que vai ser um telescópio que vai ser construído para fazer várias espectroscopia, também, talvez. Tudo é talvez, entendeu? Mas tem que ter alguém que escreva o Science Case. O Science Case do WST que eu escrevi é bojo. E aí você vai conseguir ir lá e medir o quê? Não as Giants, mas você vai ter telescópio suficiente para baixar e entrar no Main Sequence Turn-Off. Quando você entrar no Main Sequence Turn-Off, você pode usar isochrone ages. Aí você pode ter dados de estrelas no bojo, né? Os chemical clocks é difícil, porque você vai ter que ter para um monte. E você vê, esses clusters aqui estão aqui perto. E a pessoa usou o NOT telescópio. Tem 7 estrelas por cluster, 6. E já foi considerado. Nós estamos em 2021, né? Então, é muito lento, né, o processo. A gente sabe o que a gente quer, mas a gente sabe quanto demora.
More questions? I think over there I have one. Take the microphone, yeah. Slide 2 for that, yeah, okay. Go ahead. Huh? Oh, no? Okay. This side now.
This side.
Girls, students. So, yeah, I have a comment about yttrium-magnesium. This is from Edvardson. It's a long time, this work with yttrium. All the stars in your plot stop at the 4 giga-year. You have no old stars, right? So, of course, I keep in mind that this could be good for old stars, but we don't know, right?
No, now we know, because I have this is what I'm going to show in the colloquium. Now we have a data set after Gaia DR3, because Gaia DR3 happened last year. And we have a very good sample of stars for which you have, I call this the creme de la creme sample, is the one where the parallax is fantastic. And so for this fantastic parallax, my distance are at 1% level precision. And so the isochrone levels, the isochrone aids come to around 10%. Of course, the precision, accuracy is difficult because it depends on the stellar model. But that means that for that sample, we extended, to see if our ages were coming out meaningful, we extend the yttrium over magnesium up to oldest ages, and it matched perfectly the ones of Nising, because Nising had made this for a very nearby 74 stars, for very high quality that he had, and he got this extended. No? Here with the clusters, you're right, you can only see but you see beautifully. It is beautiful, yeah. And it goes up to 12 or 13 giga-years.
Okay, good. So the dream is one good spectra for each star in the galaxy, right?
So you don't need, because you have the different things. So it depends. Now it's like, what's your question?
Yeah.
You see? Then I can tell you which is the data you should use to figure out this question. The problem is to have enough people, right? Because data we have,
These young people probably you do that. Mais alguma questão? No? Let's thank you, Cristina, again.
Thank you.
So, time for coffee break, right? So see you next